mechanism for this reaction. How do we know which one is going to be the major product of this reaction? The first thing we're going to look into is the Lewis base used for the reaction. When we have a weak Lewis base, in this case we are talking about water, carboxylic acids, and alcohols. Those conditions favor always unimolecular mechanisms. Remember, those reactions are called solvolysis reactions. The solvent is also the Lewis base. In this unimolecular mechanism, the slowest step is formation of a carbocation, which is the same slowest step for both nucleophilic substitution and elimination, and because of that, they always coexist. Therefore, whenever we use weak Lewis bases, we will get a mix of nucleophilic substitution product and elimination, since once again they go through unimolecular mechanism. Nucleophilic substitution is usually and mostly the major product of the reaction. The major elimination product, remember, will be the most stable alkene, the one with the highest substitution. And we also learn here that this reaction goes faster with tertiary halocalkanes and secondary halocalkanes because those are the ones forming the most stable carbocations. We discussed carbocation instability. Remember the factors affecting carbocation instability: inductive effect, hyperconjugation effect, resistance. We will never see a primary halocalkane reacted through unimolecular mechanism because methyl or primary carbocations are never formed, too unstable. This will only happen if you have a potential rearrangement happening from the primary to, let's say, a tertiary halocalkane. So in summary, whenever we use a protonated Lewis base, water, low molecular weight carboxylic acid, or alcohols, we should be thinking about unimolecular mechanism with a mix of SN1 and E1 products, SN1 being the major. On the other hand, when we use a strong Lewis bases, those are negatively charged, quickly we should be thinking about bimolecular mechanisms. The bimolecular mechanisms that we learn are SN2 and E2. So one wonder, okay, we use a strong base, we have a bimolecular mechanism, but then now do we have an SN2 or an E2 mechanism? Remember, SN2 and E2 are two independent mechanisms. They compete, but they don't coexist. So there could be conditions in which one of them is highly favored. So once we know that we have a strong Lewis base, once we know that we're talking about a bimolecular mechanism, how do we determine if we have an SN2 or an E2 reaction? Next thing we're going to do is to focus on the nature of the haloalkane. If we have a primary haloalkane with a strong Lewis base, the reaction that most likely is going to be is an SN2 reaction. Very fast reaction for primary haloalkane on a strong Lewis basis. Only two exceptions for this. If you use as a base potassium dibutoxide, which is a very bulky base, it's never going to do SN2, then that will lead to an E2 product. Elimination, and in this case, because it's bulky, remember the major elimination product will be the least substituted alkene. Sorry, okay? Because of the base being bulky, once again, E2 is the major, and the radial activity favors the lowest substituted alkene. If we use sodium amide, we will also favor E2 elimination. What happens if now we have a secondary haloalkane? What is the dominant mechanism? Well, secondary haloalkanes can react by both SN2 and E2. Remember, guys, for by molecular nucleophilic substitution, the factor controlling the reaction rate is static factors. That's why primary reacts so fast in SN2, and that's why primary haloalkane mostly lead to SN2 products. Secondary haloalkanes are kind of in the middle, so they can both react through either SN2 or E2 mechanism. So what determines if the reaction goes through SN2 or through E2? Well, if the Lewis base is a better base, it will lead to elimination. If it's a better nucleophile than base, to substitution. How do you know that? Well, simply, you have to think about the conjugate acid. So any Lewis base with which conjugate acids has a pKa below 11, those bases will favor SN2 with secondary haloalkane. Those Lewis bases with conjugate acids having a pKa larger than 11, those Lewis bases will favor E2 elimination. In this group, we basically have hydroxide, alkoxides, amide, acetylides. It's a small group. Everything else usually favors substitution. This group over here. And finally, whenever we have a tertiary haloalkane in the presence of a very strong Lewis base, the only mechanism possible will be E2. We will never have an SN2 reaction over a tertiary haloalkane because it's too bulky. Also want to remind you a couple of things about these two mechanisms. Remember that SN2 is a backside attack. So if you're talking about a secondary haloalkane, which is chiral, the product will have reverse configuration because of the backside attack. In regards to E2, you need to remember that for E2 reactions to take place, the haloalkane must be in a reactive conformation in which the leading group and the hydrogens for the elimination must be anti-coplanar, and that will determine the stereochemistry of the final product. That is the reason why the reaction is stereoselective and is also stereospecific. For cycloalkenes, anti-coplanar translates into transdiaxial, and that will also determine the stereochemistry and the regioselectivity of the elimination reaction. In terms of regioselectivity for E2, remember that usually the most stable alkene is favored, which is the one with the highest substitution. Also, I wanted to remind you that you will always get as many E2 products as non-equivalent beta hydrogens you will find in the molecules. The same happens with unimolecular elimination. And something that I didn't mention, but also remember that for unimolecular mechanisms, because the slower step is formation of the carbocation, there is always the possibility of rearrangements happening whenever a most stable carbocation is formed. Okay, so as a summary of this, you first focus on the Lewis base. If the Lewis base is weak, you're going to think about unimolecular mechanism in which both SN1 and E1 are coexisting, SN1 being the major. If you're thinking about a strong Lewis base, if you have a strong Lewis base, you must think about a bimolecular mechanism, SN2 or E2, and in that case, the nature of the haloalkane will determine either SN2 or E2 will be the major product of the reaction. Now, if you know this and you know the features of each mechanism, you will be able to predict not only the product, but also the right stereochemistry and the proper regioselectivity for each one of these reactions. Thank you.